Good morning, everyone. I'm Christina Corbane from the Joint Research Center of the European Commission in Italy. Today, I'm going to talk about an experimental research. So it's not about field work, but more work behind the computer. So this experimental work explores the relationship between crisis SMS that were sent in the aftermath of the Haiti earthquake and the building damage derived from remote sensing data, to see whether near real-time SMS can help in diagnosing the spatial distribution of the building damage. As you already seen, after the earthquake, Haitians could send SMS messages on their locations and urgent needs through the online mapping platform Ushaidi. More than 3,000 text messages were mapped almost in near real time between the 12th of January and the end of March. In the meantime, the remote sensing community was working on the assignment of damages to buildings using aerial photos. Each building was assigned to a damage grade. Grade 1, for example, for no visible damage, 3 for very moderate damage, 4 for very heavy damage, and 5 for destruction. The outcome of this collaborative effort was a detailed building damage assessment that was shared with the Haitian government 2 months after the earthquake in support to the post-disaster need assessment and recovery framework. So in order to see whether the geolocated SMS can be used as early indicators of the damage, we first analyzed statistically the interactions between the patterns of SMS and the building pattern, and then we identified a suitable model for predicting the damage intensity using the SMS locations. So we had to consider the geolocated SMS and each individual building as marked spatial point patterns, with marks corresponding either to SMS or to damage grades from 1 to 5. So the relationship between the two distributions can be identified in terms of attractions or repulsions. The observation window was on the area of Port-au-Prince, and building damage grades 4 and 5 were merged together because they both represent buildings that are very heavily affected and that are beyond repair in a reconstruction sense. So this synthetic representation of building points grouped into cells of 0.3 by 0.3 kilometers shows a clear clustering of the building damage pattern. The same can be said about the patterns of the SMS. However, to better characterize the spatial structure of these two distributions and the interactions, we use the famous key-replay function. It allows to identify statistically significant clustering or dispersion of data points by comparing them to the pattern of to the distribution of a random pattern. So for studying the patterns of SMS and buildings separately, we used what we call the self-K function. And for the analysis of the interactions between the two patterns, we used the cross-K function. So the results of all these analyses using these K functions showed that actually buildings that were assigned to damage grade 1 and 3, which is no visible damage and moderate damage, showed a completely random pattern, no significant clustering or dispersion. Whereas the buildings that were assigned to damage grades 4 and 5, so very heavily affected buildings, showed a significant clustering of the buildings. And also, the geolocated SMS showed a very high and significant clustering. This encouraged us to study the interactions between the two patterns of very heavily affected buildings and the SMS. So the results show that there's a significant positive correlation between the two distributions, and this attraction was observed at distances ranging between 1 to 3 to 4 kilometers. So these interactions could be actually used to model the distribution of building damage intensity. So for that, we had to use or to choose an appropriate model that could take into account the interaction structure. And so the most attractive model seemed to be, sorry for the name, but Gibbs point process. So this model allows actually to predict the building damage intensity using the interaction structure that was identified previously. So for fitting the model, we used all the SMS locations in the window of observation and a subset of the building damage points. Then the fitted model was used for predicting the building damage intensity over a regular grid. You can see here the observed damage intensity and the predicted damage intensity and see the similarity between the overall patterns. An analysis actually of the correlation between the predicted and the observed damage intensity values showed that the Gibbs model allows an accurate estimation of the spatial distribution of very heavily affected buildings. Deeper analyses are currently being implemented in order to see the effect of other explanatory variables on the precisions of these predictions. Examples of these explanatory variables could be the total building density or the rubble index that we derived from remote sensing data. The accuracy of the geolocation of SMS, which is mainly based on street addresses, is also being analyzed. As you can see, SMS are mainly clustered along the main roads, suggesting a limitation in the geotagging of the SMS and a strong dependence on the OpenStreetMap coverage. So finally, this work has the particularity of exploring for the first time the relationship between crisis SMS and the remote sensing-derived building damage assessment. So it showed that crisis SMS can help in organizing the remote sensing effort by focusing the damage assessment on the most affected areas. So thank you for your attention.